applies to me. So today I will tell you a few things about a range of subjects which I think you'll find useful in the future. The first one will be a very superficial overview of some changes in HTTP2. As many of you may probably be involved in the development of web systems in the near future and in the distant future, it will be handy to know what the differences are. Has anyone been following the development of this protocol? So there is another protocol known as SPDY, and you're supposed to pronounce that as speedy. It has been developed by Google and implemented in some earlier versions of the Chrome browser. And eventually, it has evolved into what people refer today to as HTTP2. There are several basic differences that make it a better protocol than HTTP. It might have some disadvantages as well, and you'll think about that shortly. So the first one, the first distinctive thing that makes it different is the fact that it uses one connection and I will visualize this in contrast with HTTP, the regular protocol. So you know that if you're a client and you're a server, you send a GET request. The server processes it and sends you back a response. For example, this could be the index page. Then your browser analyzes this HTML file. It finds references to images, JavaScript, CSS files, etc. So it prepares a list of things it needs to render the page. And then for each of them, it sends another GET request, and then another one, and so on. So if your page has, so besides the index page, you have 1, 2, 3, 4, 5 images, then you will have 5 more additional GET requests. And you have to remember that every single GET request has to establish a TCP connection. It's a heavyweight protocol with a lot of complexity. You remember all of those timers. They have to be very precise. You have to have buffers. You have to keep track of the state of your connection. So each of these lines is one of those. And you also remember that it's a connection-oriented protocol. And inside each connection, when it happens, you have to do a 3-way handshake. So you have to make 1, 2, 3 full trips to the server before you can actually transfer any data. Now you multiply this by this, and you realize that on a modern web page, you don't have just 5 images. It's full of anything. Advertisements, like buttons, JavaScripts that do a lot of things in the background. And that causes the web page to load slowly. Of course, when you look at it with your naked eye, it might be fast. But if you actually use some mechanism or a tool to measure how long it takes, you will see that a lot of things happen in the background. Some browsers try to reduce this problem to a smaller one by doing things such as keep alive. So it doesn't establish 5 TCP connections for each of them. It has one connection, and it's being reused when this resource is retrieved and it moves on to the next one through the same TCP connection. So that reduces the cost a little bit. Another thing a browser can do to make it faster is they can have multiple connections. So you have one here, and they can work in parallel. As a result, you can retrieve images and JavaScript and CSS files in parallel. And to the end user, this looks like, wow, this page is loaded really, really fast. So there are some tricks that HTTP 1.1 and 1.2 servers can employ, and clients, of course. There are a few tricks they can employ to make the user experience better. But still, it can be made even better than that. So, in contrast, HTTP2 uses a single pre-established connection, and I don't remember the official terminology for it, but if anyone has worked with a protocol known as AMQP, you have multiple channels over one single connection. So that's what HTTP2 does. Basically, you can have multiple streams going through the same pipe. And each stream has its own identifier, so you know which data belongs to which substream in this connection. And the obvious benefit is that you don't have to re-establish a TCP connection for every single resource. You have just one. And you keep it open for as long as your session lasts, or for as long as there is stuff to transfer. Another benefit that this protocol gives us is what they call server-side push, or server push, or you can just call it push. And what it does is the following. Now, if you look at this thing on a single timeline, let's say this is how long it takes you to send your GET request. This is how long it takes for the server to figure out what you want and give it to you. This is how far you get when you actually receive the server's response. Then you begin to parse it, and you build this list of other things you want, and let's say that it's here. So this is how long it takes for you to begin requesting new resources. And for each of them, you send another GET request, so it goes on and on. Based on common sense, you could make a prediction that once the person receives this index HTML page from me, they will also request the images in the page, and the CSS scripts and the JavaScripts. So what if I will just give it to them right away without waiting for them to ask me for those scripts? This way, we can save some time. And this is what the server-side push is about. When it sends you this answer, it doesn't send you just the HTML file. But once it's done, it uses a marker to say, and this is one other thing which you will most likely want. And it could be a CSS file that is included in the web page, an image, and so on. In other words, with server-side push, you don't have to wait. As a server, you don't have to wait for them to ask you for this image. You give it to them proactively without waiting. And do you think this is a good thing or a bad thing? Maybe it has some disadvantages. Dorian, what's the advantage of this?
The advantage is that it will load the page faster. The disadvantage is that maybe the user will consume more traffic, for example. If server will push some information which
you don't really need.
Not need
for example, if I am using an ad blocker,
yes, and I don't want this
advertisement anyway, but it will send it to me. Okay, it makes sense.
Using a mobile phone, they're very expensive. Internet is very expensive. Maybe some.
But if you were using a mobile phone with a regular HTTP 1.2 server, what would happen? Your phone would connect to the server, it would get the HTML page, and then it would send more GET requests for each of those images and other resources. And in fact, you would waste more traffic because it wouldn't just get the image, but for each image, it would prepare another GET request with all those headers in it. So on one hand, you say it's going to be a potential waste of traffic, but on the other, it's more conservative. Jan, what do you think about this change? Is it a good one or a bad one, or none of the above?
I think this is better than the previous one.
But what are the disadvantages?
I think it requires more, not time, but
Patience?
no.
Money?
No.
People?
Yes, memory.
Why?
Because we use this delta also requires memory.
Which delta? This delta?
Yes.
Well, let's add some labels here so we can use proper names. So this one is when you send your GET. This one is the server processes your GET request. This is server sends response. And this one is where you process the response. So which of them will take more memory in the case of HTTP2? Well, she said it, so maybe she... Well, yeah, you gave her a suggestion.
I suppose that if a server gives you a response just with index, it's smaller. But with info, it's a lot of space for this info, for images, for...
Yeah. Is it clear what push is about? Would you like me to explain it in some other way, analogy or more examples? Okay, so HTTP gives us server push mechanisms. Another thing it does is header compression. You may have observed that in the content type or content encoding attribute in the response header or request header, you could have, there is a way to indicate that you are willing to accept compressed responses. So what happens is that when the server receives such a request, it says, this client just indicated that it is able to receive compressed data. So I'm going to send this index HTML not as is, but I'm going to compress it first and only then send it. As a result, if this thing is originally, for example, 1,000 bytes, it could turn into something like 30 bytes. So when it sends the response, it will have a response header and then the payload or the body. So the body is compressed, but the header is always, uncompressed. You see all those strings such as user agent, content type, content encoding, accept languages, cookies, there are many, many, many requests, attributes in those headers. With HTTP2, they also introduced header compression. And when you think about it, it makes a lot of sense. And here's why. Keep in mind that every time you send this GET request, you always send the same string. For example, remember when we examined behavior of those proxy servers? And there was a user agent string, which contained a lot of text in it. Well, that long line of text is always a part of every single GET request that your browser sends. Even though if you're the server and I'm the client, I spoke to you just 5 seconds ago and you already know this long string, but if I'm going to request another resource from you, I'm going to tell you exactly the same thing. My user agent string is blah, 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 and something really, really long. And that causes waste. Now, given the fact that you have a single TCP connection, which is maintained alive for a longer period of time, you can rely on this context to compress things in a much better way. Now, I will make a little detour. In some course, you probably studied a compression algorithm, which was the Hoffman algorithm, which builds a tree. And you remember that in the end, it produces something that you could refer to as a dictionary. So you have a very long, well, not necessarily a very long, but you have a pattern of input data. For example, let's say this long string has 20 letters in it, and you replace it with something much more concise. For example, alpha. And then you take another frequently used string in your text. You take that and you encode it as beta. And so on. You build this dictionary where on the one hand you have the original data, and on the other hand you have the concise representation of the same data. So you have this dictionary, and the person who wants to decompress the data has this dictionary as well. When you send them your message, it's not made of this, but it's made of that. For example, it could say alpha, alpha, beta, alpha. And the person looks in the dictionary and says, I have to replace alpha with this, and this alpha with that, and so on. So they re-establish this bigger message. So one of the side effects of the fact that you have one connection which is used and reused is the fact that you have computed this dictionary and you can keep using it throughout your entire session. Whereas in this case, when you had a single TCP connection for every resource you requested, whenever you would compress your data, you would have to build a new dictionary for each of those connections. So that will consume more CPU cycles, and in the long run, it would be a waste of resources, because every time you will be compressing things such as the user agent string, which doesn't change because your browser is a constant thing, or the accept languages header. It is always the same. It doesn't change throughout time, unless, of course, you update your browser settings. So with header compression enabled and the continuous reuse of the same TCP connection, you actually save a lot of traffic because compression gets more efficient. Does this thing have any side effects, in your opinion? Any drawbacks?
When a user changes some settings, how they can tell that they modified something? They have to change the dictionary.
No, they will just, well, of course, yeah. The browser will send a new user agent string, for example, and the compression algorithm will see that and it will recompute this, at least partially. However, I don't think that the user agent string changes so often that you really want it to be done on the fly while this TCP session is alive. What about convenience for programmers? Does it have any impact on that? Yeah. For example, last time when we were comparing different proxy servers, you used a network sniffer and you sniffed the traffic, and you could just look at it and say, oh, this is where I added this. But now, when you compress it, it will not be human readable text any longer. Unless, of course, you can decompress data with your eyes, like they did in the Matrix with all those green letters flowing down. So from this perspective, you have a little usability issue for the programmer. Yeah?
Isn't it safer for the user who sends the message? This way the hackers won't see the information.
Mm-hmm. No, it has absolutely nothing to do with safety. And here's why. On one hand, you might see this. For example, let's say you send a GET request that has the user agent header attribute, and it's set to some value, for example, X. Now, if I use a sniffer like Wireshark, this thing will be sniffed. I look at it and I say, aha, this person uses user agent X. And hypothetical, let's say we know for a fact that someone in this room sent this request. We don't know who it is, but just by looking at your browsers, let's say he uses Internet Explorer, Opera, and Firefox, and this is Firefox, then I can say, aha, it was him who sent this request. And if it contains some sensitive data, perhaps I can do something against him. So this is what you can do with HTTP 1.1 and 1.2. With HTTP2, this string wouldn't look like that. It would look like some, let's say, whatever would be the compressed version of this text. And I look at it, and of course it has nothing to do with this. And if the person looking at that would be my mom, then of course you would be safe. But if it's a person who has read the RFC, they know that this thing is compressed with the following compression algorithm, and the dictionary was computed as follows. Then for them, it will only take one little bit extra effort to decompress it and turn it into that. So compression is not secured. Its purpose is to simply save space and bandwidth. If you want it to be secure, then you have to use encryption. Which is a completely different matter. It's a topic we will discuss in great detail in our upcoming course. So, yeah, that's how I respond to your comment. One more thing that I have to emphasize is that it tends to be backwards compatible. And here's why. Once you have established this long-lasting TCP connection that uses multiple channels, and with all these bells and whistles, like server push and header compression, when you do decompress it, it looks like plain old HTTP 1.2. Or 1.1, whatever the current version used to be. In other words, is this making sense, what I just said? So basically the idea is that once you decompress the headers, your HTTP communication will look like old HTTP communication. Now my next question for you is, how does that impact web applications? The fact that HTTP2, when you look at it deep inside, uses the same syntax and notation as the previous version.
Backward compatible?
Yeah, backward compatible. So let's slide into a slightly different realm. You've heard about HTML5. Who has not heard about HTML5? Okay, so there is this thing HTML which you've seen on a daily basis, and it has multiple tags and the syntax which you're familiar with. Well, there is this thing known as HTML5, which is an attempt to standardize the tags, add some additional functionality such as, I don't know, maybe WebSockets, Canvas, SVG file support for rendering vector graphics, etc. And the problem with HTML5 is that not every web developer is actually creating websites that are proper HTML5 compliant. Why is that? No one does any web technology work? Well, this silence has to be interrupted by someone, and I guess it's going to be him.
I don't know, I think it's because of the new syntax introduced in the HTML5, which want to be recognized by older versions.
Okay, that's one argument. So actually this problem is quite complex because on one hand you have multiple browsers and they don't all support HTML5 entirely. So if you want your website to look good, you can write it in pure HTML5, but then in Internet Explorer 8.7, it will look like this. So you have to perhaps chip away something from this side, but make it more acceptable to a greater audience. Yeah?
But doesn't the other browsers like Internet Explorer, Safari more standardize on the new HTML5?
Yeah. The browser developers are trying to make things better, so they strive towards the standard. But then think about this. Imagine you are a web developer who has studied HTML 6 years ago. You've learned a few tricks, they work. What's your incentive to rewrite your site or to update it to be fully HTML5 compliant? Why should I exert any extra effort if the browsers already render my site in a human readable fashion? So there is a lot of inertia. People are lazy. Maybe some of them are just not smart enough to fully understand what HTML5 is about. Or maybe they're not lazy and they are smart enough, but their boss says, don't waste your time making this, you better work on this new product. Because if you already have a site that looks good, there is no added value in porting it to HTML5. There is no business rationale for that. And as a result, the transition to HTML5 is a very slow process, which is going to take a long time. And it has been in progress for a long time. Do you think this will be the same with HTTP2? Will it be one of those new protocols that are very, very slow to be adapted by the community?
I think if Google will push it
Mm-hmm.
hard enough, it will stick quite fast. However, it will take time to implement the servers. It will take time to implement the clients for HTTP2.
Mm-hmm.
And if HTTP2 will have this ability to tunnel HTTP 1.1,
Mm-hmm.
maybe it will be easier.
Well, that's what it does. Like I said, it's backwards compatible. You have a comment?
I think it's easier to update the web server than updating the code. That is a lot of job to do.
The code of what?
For example, we have a lot of CSS file,
Mm-hmm.
which is distributed, designed for the Internet Explorer for the other browsers, and in HTML5 there's another standardization which is not in the previous version. But about the HTTP2, we have only to update the web server.
Mm-hmm.
That's all. It will just.
That's right. I'm going to visualize it to make it easier for others to understand as well. So if you think about the problem in terms of stakeholders, which parties are involved? In the case of HTML5, you have the web server, the web browser, and millions of different websites created by thousands of web developers and programmers. So let me draw some people here. Now, HTML5, the web server doesn't care about it. It's just a file that it will send. So what is important is for the web browser to be able to support it. And web browsers, you have, let's say, 10 dominant browsers developed by some teams of programmers. So this is one party that does care about HTML5, the browsers and the browser developers. And the other party is this web server, website and the millions of people involved in creating all the websites on the internet. Each of them has to one day get up in the morning and look in the mirror and say, you have to update your site to HTML5. And expecting millions of people to do that right away is a quite naive thing to expect. But when it comes to adapting HTTP2 as a standard, then it is, of course, affecting the web server. It has to be able to talk in HTTP2, so they are involved. And the web browser as well, because the web browser must be able to form requests that the server will process according to the protocol. However, all the millions of websites on the internet and all the millions of people involved in making those sites, they don't have to change anything in the logic of their web application, because HTTP2 is backwards compatible in terms of how headers look like and which values they have. For them, HTTP2 is just a transport layer. Well, it's just a thing they use as transport for the payloads. So they don't have to update anything on their end because of this. And it's much easier to mobilize a few teams of people who develop web browsers and a few teams of people who develop web servers. There are not millions of web servers out there. There are a handful. Apache, Nginx, Microsoft's IIS are dominant web servers, and then other ones are, smaller, less popular, but still they are around. And it's the difference. Another difference is that the people who work on this and who work on that are usually much more sophisticated, organized, and better equipped than the people who create these millions of websites. Anyone who picked up a book about HTML can already, make some very simple website. It doesn't take a lot of dedication and effort. And based on this, it is not unreasonable to predict that adapting HTTP2 will be a much, much smoother process, and it, in theory, will be swift. Do you agree? So this is my high-level overview of this new protocol. Do you have any questions about it? It's already released. In fact, let me double check that. And some browsers have had support for it for quite some time already. Let's see. Okay, so let me tell you a few things. First of all, the official way to write it down is HTTP/2. And it's defined in RC 7540, which was published in May 2015. So it's this month. So it's really, really fresh. However, keep in mind that it's based on Speedy, which has been around for longer. So let's see who supports it. Chrome does. Chrome for iOS. Firefox. It has had support for HTTP2 since version 36. I don't know what the current one is. Internet Explorer supports it in version 11. By the way, it has been renamed, well, maybe not renamed, but discontinued, and now they have a new browser, which they call Microsoft Edge, and it will be released along with Windows 10 sometime this summer. Opera supports HTTP2 as well, as of version 28.
What about web servers?
Okay, let's see. IIS supports it in Windows 10, which is a beta.
There is the test web page for HTTP version.
IIS 7.
Well, it says whatever IIS is shipped with Windows 10 beta. Well, we could just look it up on Microsoft's web pages. So let me give you some highlights. Nginx has a module that provides experimental support, and they plan to release it by the end of this year. Apache has had support for some Speedy while it was still worked on, but it doesn't yet officially support HTTP2. So as you can see, it's not yet happy with mainstream support by web servers. However, keep in mind that it is this month when it was officially finalized and released as an RFC. So it will take a while, but it shouldn't be a long while. One more thing. You mentioned encryption, or I mentioned it because someone made me say it. In the context of discussions about what HTTP2 should look like, some people stated that it should provide and enable encryption by default. So everything should be encrypted and that should be mandatory. However, this was not something that made it into the final version of the RFC. So, of course, it does support encryption if you want it, but it doesn't make you use it even if you don't want it. With that said, what are your questions about HTTP2? Other ones. You've asked about browser support, server support. What else would you like to know?
As I understand, it won't affect us as application programs as much as...
It shouldn't. Only to the extent that from now on, you won't be able to just use Wireshark to sniff it. You will have to probably do a little bit more if you want to see the headers.
Probably a new version of Wireshark
We'll take care of that. Yeah. Wireshark has this thing known as a dissector. It's a little parser for any given protocol. So it takes raw data at the input and it parses it, and it transforms it into that very nice human-readable representation that you're familiar with. So I'm not going to be surprised if shortly, or maybe if it hasn't already been done, if someone comes up with a dissector that makes HTTP2 look human readable. Anything else? Okay. In this case, I clear the board and we move on to the next subject for today. How long until the end of this class? 10 minutes. Mm-hmm. The next subject is about securing communications. And I will tell you about a few tricks. And when we do have that class, when you visit me at work, I will show you some of these things in practice. We could do this today as well, if we could move on to another room with a projector or a bigger screen. Or if there are not that many of you, I can just show it on my computer and yeah, maybe this room behind us is free. Has anyone ever experimented with SSH tunnels? So one person. Anyone else? Mm-hmm. Who has used SSH? 2 people. SSH stands for Secure Shell. Okay, apparently some people have used SSH but didn't know they were using SSH. It stands for Secure Shell, and it's a protocol that enables you to remotely connect to a computer and run different commands on it without actually being there physically. So that's what it's about. It has a lot of interesting features. One of them is tunneling. With an SSH tunnel, you can do some very, very interesting things. So let me make a drawing of a hypothetical scenario. So this is the internet, the most unsafe place on the planet. And this is your home, or no, let's make it a bank. So this is a bank. And in this bank, they use a program that does some network communications over a network. This program has been written sometime in the 80s. The people who wrote it are probably retired. Some of them might be even dead. But if they are alive, they really don't want to do anything with this program. The source code was lost. There's no documentation, but it works, which is a good thing. In the 80s, they built really reliable software. And this program was designed to interact with another machine. And for as long as they were in the same local area network, within the constraints of the premises of the bank, everything was fine. But now, with progress, the bank grew, so they don't have just this building, they have a lot of other departments across oceans, across continents. So the bank grew much bigger. Now, this program has to talk to this program here. And this thing now must reside in this bank, which is a physically different location. Now, they do have a connection, but it goes through the internet, the scariest and most dangerous place on the planet, where anyone can use Wireshark to sniff your traffic and see what this program has to tell this one. Bank transfers, account details, personal data, amounts of money, what kind of things you're buying, drugs, guns, computers. And of course, the bank doesn't want anyone to know what this program is telling the other program. How can we solve this problem?
By using encryption.
Using encryption. So encryption is something that you could treat as a black box that does several things. It takes some text at the input. It takes a secret, some kind of a password or a key. It processes it, and at the output it gives you a cryptogram. You could also call it a crypto, which is this text encrypted with this key. So if, for example, at the input I say hello and the password is 12345, and then at the output, instead of hello, it will give me something like %53x. Doesn't make any sense, but if you take this, you give it at the input, and you give it the same key, then at the output it will say hello. So that's encryption. Now, the problem is that this program, you have an executable file. It's a compiled binary file. You don't have the source code. So if you want to add encryption, you would have to update the program itself. Let's say this is its code. And in order to teach it how to do encryption, you would have to extend this code by adding some more functionality to it. But like I said, it was made in the 80s. The person who wrote the program is not available any longer. There is no source code. Moreover, the people who run the bank are really, really afraid to make any changes, because this thing has been working correctly and flawlessly for 35 years. If it's not broken, don't fix it. They fear that if you make any single change here, you might have some bugs which will result in loss of finances, compromised bank accounts, or something else. And they don't want to take those risks. So you say, yes, you have to use encryption, and you're right, but you cannot change the program itself. You can do something else, perhaps. Then,
maybe you can somehow track the IP address that sends you this request.
and what else?
Find out that someone is trying to pretend he is another user.
What do you think?
We can try using VPN.
Okay. VPN. I am going to write it down.
As I understand, we have to make sure that the computer right there sees the other one on the other side of the planet, like on the same network, yes?
Yeah. So you can do this with the VPN. I will tell you more things about that once we're done with this. What else can we do? Perhaps if you have already finalized your lab with Quick Chat, you already know how to do some basic reverse engineering. So why not just take this program, use a sniffer to see what its protocol is, and then write a completely new program that implements the same protocol, but with these bells and whistles added. It could be done. Just keep in mind that reverse engineering requires a lot of effort, and
It's not always perfect.
it's not always perfect, because even though you've spent many hours looking at Quick Chat logs, can someone say with 100% confidence, I am sure I've implemented the whole protocol? Why not?
Because there could be another stuff which user didn't know that there could be, or there is another, or the algorithm he thought is correct, it's not the correct one.
Okay, so it could be the case that whatever you thought the program was doing was actually something different. It could also be the case that there is some other message that you haven't ever captured with Wireshark because it was never sent, because in the program you would have to press some magic combination of keys to invoke that functionality. And because you didn't know about it, you never observed it, so your re-implementation of the protocol will actually be just an implementation of a subset of the original version. And I could also add another argument. It could be that this program was made in the 80s and it cost $50 mega. Really, really expensive. And of course, you could reverse engineer it, but if it cost that much to build originally, reverse engineering and doing it again will probably cost just as much. And the bank might say, you know what? This is way more than we can handle. And then another option is to use an SSH tunnel. So how does this work? Let's say you have one computer here and another one here and the internet between them. In simple terms, this protocol allows you to establish a secure connection between these two computers, which uses encryption. So anyone with a sniffer here won't be able to do anything with that data. And once this secure connection is established, I'm going to draw it as a pipe. So you have this pipe, and you have a bunch of programs running here. You can configure your SSH connection in such a way that any of these programs, when they connect to, let's say this is this computer's address, it's going to be 1897.56.110. It's the address it has on the internet. And besides that, it also has a local host interface, like any other one. So you can tell this program, for example, that if it connects to this interface at a specific port number, for example, let's make it port 55, then this connection will be automatically tunneled through the SSH connection, and it will get out on the other end, And you can also specify where it goes once it gets out. It could be, so let's say this computer has another IP address, 95.112.50.5, and it of course has a local host interface as well. So you can have this program here connect to 127.0.0.1 port 55, and when this connection is established, it's tunneled through SSH, and once it's on this computer, it's redirected to, let's say, this interface port number, it could be 55 as well. But I'm going to use a different number just to make sure you don't think it has to be the same number on both ends. Now, imagine that this program is this one, and the program listening at this interface on the other computer is this one. So from the perspective of the software, it establishes a TCP connection to this address and port number, which would be the same thing as establishing a connection to this address and port number. And from the perspective of this software, none of its communications are in any way different. It sends exactly the same messages in exactly the same format to this interface. And then using SSH multiplexing magic, this data are transferred through the tunnel, which is encrypted because SSH uses encryption. And when the data gets here, it is put into another address and port. So the program that listens at this interface has the illusion that it received it like any other regular connection. It doesn't know that it came through the tunnel. What it does know is that if it looks at the source IP address in the IP packet header, it will see that the source is equal to 127.0.0.1. Is it making any sense? I guess it will make more sense when I hook up my computer to a screen and show you how this works in practice. Remember in the previous exam that I gave you, there was a question with netstats output and an FTP server listening for incoming connections only on the local host interface. And the question was, can this FTP server accept connections from home or something like that? And your answer hypothetically should have been no, because it only listens for requests coming from the local host interface. But if you use an SSH tunnel, then you can actually do this. And here's why. I'm going to redraw this here. You have one computer and another computer. And let's say that this one has a lot of services inside. It has an FTP server, a web server, and a bunch of other ones. If you exposed all of them to the internet, then all of these ports would be open. And someone with a port scanner would be able to scan all the ports and see that this one has port 80 open, port 25, port 21, blah, 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 port 22 for SSH. And then each of these ports, when they're accessible to an external person, can become an attack vector. It's like having a room with a lot of doors and a lot of windows. You have to keep an eye on all of them if you want to make sure no one is going to mess with you. But with SSH tunneling, you can close all of them except port 22, which is used by SSH, and you can keep a very, very attentive eye on it. Make sure no one connects who shouldn't be connecting. And once you establish a connection to port 22, you can connect to all of the other services on this machine as if you were coming from your localhost interface. So the difference is that to an external observer, a potential enemy, this machine, this server, is like a room with only one door. And the person inside the room has all their guns pointed to that door. If anyone comes through who was not invited, they can take them down just like that. In contrast, if you had a lot of ports open, it would be like being in a room with a lot of doors and a lot of windows, and you can only look at one door at a time, you know, like sequentially. And while I'm looking at that one, someone can get me from the back. And that's much, much more difficult to protect. So, going back to that question, you could have also said that I can connect to this FTP server from home because the server also exposes SSH. So I can connect to SSH first and then tunnel my FTP client through this SSH connection. Now let's take a break and look for a room with a projector. Hopefully that one is